heterojunction. Right, we have discussed a little bit on heterojunction yesterday, and we learned that heterojunction materials is another way of making a p-n junction. Okay, so we used to learn about homojunction, where we form our p-n junction based on similar materials with the same band gap on both p side and n side. And in this case, we are trying to form our p-n junction based on heterojunction materials, which means we are trying to combine two different materials of opposite polarity with different band gaps. So when we form a heterojunction, we should expect discontinuity at the junction interface due to the combination of a narrow bandgap material and a wide bandgap material, right? For example, if you're combining silicon germanium, so germanium is the narrow bandgap material with bandgap of 0.7 electron volt, and crystalline silicon, in this case, well, it's not a wide bandgap, but bandgap is bigger than germanium because crystalline silicon has a bandgap of 1.12. So in this case, you should expect some discontinuity at the p-n heterojunction in this case, okay? And then we also learned that in order to form a good heterojunction with a good quality, we need to consider lattice constant of both materials. So they need to be close to each other so that they are well matched, or we call them as lattice match materials or lattice match heterojunction. And in this case, we need to do a lattice mismatch in order to see how much is the difference between the lattice constants of both materials. The one that stays at the bottom part and the one that we try to grow on top, okay? So don't worry yet because we're going to learn about the fabrication in the next semester for applied student. But as I'm aware, you also learn on fabrication processes in photonic materials, right? In the previous course, I think in the second year course, if I'm not mistaken. Yeah, some of you perhaps. Ada ke belajar photonic materials which you learn about fabrication processes? Anyone? The elective photonic materials, I think engineering student got made. Any one of you took the course? Tak ada Right, tak apa, it's okay. Any pure student yang ambil course tu? Anyone? Tak ada. Rafai applied juga kan? Apply physics you pure, okay, right. So, tak ada course tu ke? Dalam elective pun, not in pure elective, okay. So I think it's in engineering elective, but that's okay. So it's okay. Kalau you dah belajar course tu, then you probably have learned a little bit on the fabrication processes that I'm trying to relate now, because if you talk about lattice mismatch or lattice match, we're talking about growing one semiconductor material on an underlying substrate. For example, if you have a crystalline silicon with bandgap 1.1, say is a p-type, then you want to grow n-type zinc oxide on top of the silicon. Maksudnya you do the film growth processes like sputtering or evaporation or chemical bath deposition or spin coating, or yeah, whatever courses, right? Whatever processes that you can do in order to deposit. So while doing the deposition, we need to know the quality of the junction, in this case the oxide to crystallized silicon. And this quality of the layer of the groove depends partly on lattice matching, right? Let's go through that, don't worry. Solid state lighting and semi-invisible devices related to that. Okay. Yes, they are related, but solid state lighting is more on the application of optoelectronic materials and devices. Solid state lighting is the core for engineering, right? Is it elective for you as well? Is it a core for engineering physics, right? SSL1 and SSL2. Elective pure. And it's a third year course, right? Is it third year course or fourth year course? Third year course, right? So yeah, it's more on the application of optoelectronic materials and devices. Particularly if you talk about LEDs, for example, then you're going to be talking a lot of LEDs. And I believe it starts from the fundamentals of LEDs, which stems from the recombination process, radiative recombination process, and then what is happening, electroluminescence, photoluminescence, all those stuff. Okay, so well, they are related, but to me, I have not gone through the SSL synopsis to be specific, but I think, if I'm not mistaken, if you compare two subjects, SSL is more on the application side of optoelectronic materials and devices, of course. Whereas for this course, physics of semiconductor devices is the fundamental for any semiconductor devices. So it's more broad in that sense, in terms of its fundamentals, but the application, no, it provides you, this course, it provides you with the right the fundamental of semiconductor physics. And then you can venture into any semiconductor devices because all of them are based on the very same principles at the physics level. Okay, so you may jump into optoelectronics like LEDs or lasers, or photodiodes, for example, or photonics. Okay, you may jump into solar cells for energy generation. You may jump into transistors, which is the ICs that we are having now in our laptops and tabs and phones and everything. And you can also go to light sensors. You can also go to, well, I think a very broad range of applications. As long as they are based on semiconductors, then they have the basic, they have the underlying principles in this course. For example, kalau you ada baca article, if you read articles on automotive punya chip kan, ada anyone read about automotive chips in the cars? Anyone read anything on automotive chips lately? Shortage of automotive chips in the cars, in car manufacturing, in automotive industry. Anyone read? Ada baca? Tak ada? Tak ada terbaca? You are too focused on your studies. You have to read, try to read as well, all the news and everything, because they are somehow related to what you're doing and what you're going to be doing in the future. For example, if you talk about automotive chips, the root cause of the shortage is in the semiconductor industry, so they are related. So in this case, to relate to your question just now, you learn the fundamentals of semiconductor, and then you learn how to fabricate, and then the application is not necessarily in the EE industry. So it may also go to automotive. It may also go to some other industries, but it stems from these semiconductor fundamentals. Okay. So you learn about the fundamentals here, but applications may be elsewhere. Okay. So when you talk about SSL just now, so the application is more on the optoelectronic kind of things like OSRAM, like Lumileds and everything. Right? All right, good. Okay, lattice constant. Let's do a bit of calculation of lattice constant. So we have gone through this list of lattice constant for a range of different materials. You can see in this table, and then we have also discussed about how do we stack uh, a material with different band gap of an underlying substrate with of different material, basically of different band gap. So, and then what if they have a big or a small difference in lattice constant? So this will result in a different level of lattice mismatch. Okay, if you have a big difference in terms of the lattice constants between semiconductor A and B, then you're going to have a high level of lattice mismatch, and this will cause strain, dislocations, defect, trap states in the semiconductor device later on. On the other hand, if you have lattice constants that are very close to each other, for example, if you look at this chart, if you see aluminum arsenide, RS, and gallium arsenide, so the lattice constants of both are pretty close. You can see they are somewhere 5.65, 5.66 for both of them. So if you do the calculation, this will result in a very small lattice mismatch. On the other hand, for example, if you want to pair cadmium telluride right on the right hand side of the chart with a lattice constant of somewhere 6.47 or 48, more or less, this point. You wanna combine the cadmium telluride with silicon with 5.43, for example, and of course that will result in a bigger lattice mismatch, right? So then, how do we calculate lattice mismatch? So do you check out how do you get the lattice mismatch calculation? Anyone? What is the equation? What is the equation that we need to use in order to calculate lattice mismatch? Have you checked? Anyone? How do we get the mismatch? So you need to try calculate mismatch, huh? How about Fatin? Fatin Nur Tahira. Fatin, can you unmute yourself? Tak boleh dengar suara lagi Fatin ni. Fatin, can you unmute yourself? Malu ke? Come on. How do we calculate mismatch? Respond for Fatin. Can you hear me? Are you there? Kavina? Kavina Cynthia. Can you hear me? How do you calculate the mismatch? Kalau tak sempat search lagi, you can search now and then share with me. Sekejap ya kan, nak do Google search. Okay, try to search now. Okay, I'll give you... okay, go ahead. I'll give you 30 seconds. It should be fast. Search now and then you can share. Difference between two lattice constant divided by lattice constant of one of them. Okay, all right. I've already said that. Okay, Savina, how about you? So while waiting for Kavina, has anybody else got another answers? Or if you want to put down the equation, you can also do that. You can write down in the chat box. Dah jumpa Kavina? You can unmute yourself, explain verbally, can be done as well. You found anything, Kavina? I think Wikipedia pun ada good. If you search lattice mismatch, then I think Wiki will also appear. Wiki is the simplest form of reference. Normally, if you are new to something, if I were the guy, I would just go to Wiki and do some reading, some background reading, and then only I zoom into more specific references. All right, Kavina said, determine by formula lattice parameter of material A minus. So it's the difference between material A and B. Okay, all right. Anybody else? Is difference of two lattice constants. Okay, difference. Is it the difference only? How do you have to divide by something? Average value of lattice constant. Okay, Nabila said difference of lattice constant divide by average value of lattice constant. Okay, so it's actually the difference. So lattice mismatch in terms of percentage. Okay, percentage is actually the difference between the more common answers that I found. Is calculate mismatch. Mismatch is, say, to relate to the physical situation here, say if you have silicon wafer, okay, then you want to grow germanium, for example, germanium on silicon. Say you are growing germanium, but germanium it has to be an epi layer. You're talking about mismatch, especially when I'm talking about epi layer, epitaxial layer. What is epi layer? Then that will be another search. So if you want to grow a thin layer epitaxial, just like what we learned in tunneling, right, yesterday, a very thin one, germanium on silicon. So in this case, germanium is the firm to be grown. A very small film nipis, very thin film. And the silicon in this case is the substrate. Okay, so the mismatch will be given by the lattice constant of your material of the firm minus lattice constant of the substrate. So in this case, the firm is germanium, the substrate is silicon, over constant of the substrate. Substrate will be the reference. Sorry ya, tulisan saya buruk sikit. Buruk banyak. So on the screen it's a bit, well, okay, so firm minus substrate over substrate. So that will give you the mismatch, right? So let's go through. For example, okay, try to calculate. Sekarang kita dah tahu this equation. We know the equation. Now let's try to calculate. If you want to grow a very thin epi germanium, okay, listen to my question. You want to grow a very thin layer of a very thin epitaxial layer of germanium on silicon. Okay, germanium on silicon, berapa persen? Dia punya mismatch. Cuba kira kat sini. Tengok lattice constant ni. Right, germanium is given, silicon is given as well. So now you try to calculate. If you want to grow germanium on silicon, what is the mismatch? Okay, you can do the calculation now. Then you can share the answer in the chat box. Let's try. Kalau you boleh buat ni, then the rest is the same thing, right? But you can calculate cadmium telluride on whatever, zinc oxide on silicon, gas on whatever. Right, cuba calculate sekarang. What do you get? Anyone? Saya pun nak kira juga. You try to calculate now. Germanium dengan silicon. Okay, 0.047. You times 100 first, Rafael, and then state the answer in percentage. You kali dulu, then you rewrite the answer. Okay, so 4.17, 4.2 lebih kurang, okay? Semua dapat kan? Just a simple math, right? There's no rocket science here, just germanium minus silicon over silicon, right? So constant of germanium 5.6, 5.658, 5658 minus 5.431 over 5.431, right? Then you times 100, times 100. Then you gotta get 4.17 lah kalau the accurate decimal places here, or about 4.2. Some even say 4%, right? So, okay, semua dapat same answer, right? Same answer, everyone. Just a simple math. There's no rocket science, no tricks, no nothing. Just a simple calculation. Kalau you dapat the wrong answer, then you press the calculators wrongly. That's it. Okay. So let me show you something. Let me unshare this and share with you a website about lattice mismatch. So you got about 4.1 somethings now. Let me show you. What if? Okay, mana api tadi? Side. Yeah. Okay, let me share with you this website. Right, can you see the website for Science Direct? About good. Right, you can come here, you can search, you can do Google search, lattice mismatch. Then one of the suggestions on the list will be this, Science Direct, blah, 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 on lattice mismatch. So it will show you different articles on lattice mismatch. So I'll just use this as an example to illustrate. So let's go down to silicon and germanium. Tengok kat sini ya. Nucleation control growth silicon germanium, germanium on silicon 100. Lattice mismatch between germanium and silicon lattices is 4.2, 4.17. So correct, right? This is now your calculation. So we are talking about growth of germanium on silicon 100. So you learn about 100, 111, 101, all those stuff in solid state physics, right? The crystalline orientation. And we also learn in this course as well during the beginning. So that's about 4.2%, right? So it's the difference between 5.6 just now minus 5.6 plus minus 5.4 plus over 5.4 plus times 100%. So if you go up on this page, I'll share this link in the chat box. Nanti you can just have a look. Okay, let me just share this. You can now click and see for yourself. Okay, I've shared already. So if you come here, the top page, the top on the page, top part, you can see mismatch between gallium nitride and zinc oxide is 0.017. Then you can also see the mismatch between gallium antimony and gallium arsenide is about 7%, right? And look at the comments here. Makes it difficult to grow high quality materials. So this is the implication as we learned yesterday. Remember the strain lattice and everything. So it's not going to be easy, and it's not going to be a perfect growth. It's not going to be a good crystal quality because the mismatch is relatively high, 7% between gallium antimony and gallium arsenide. Okay, you can just scroll down and see many more references given here. So for example, mismatch between mercury telluride and cadmium telluride is only about 0.3%. Okay, so this allows epitaxial growth of high quality mercury cadmium telluride firms on IR transparent cadmium telluride. So mercury cadmium telluride on cadmium telluride. Okay, so when you talk about binary or ternary or quaternary, you can alloy. You combine more than one element. You can also, when we talk about growth, you can also vary the fraction of the atom in the compound. Okay, For example, macam ni lah, cadmium, for example, for this case, cadmium, zinc, telluride. So you can also vary the fraction, we call it molar fraction of this cadmium and zinc in cadmium, zinc, telluride compound. Okay, so in this case, so it states here Z is about 0.004, so that means cadmium here is 1 minus 0.004, and zinc is 0.04, right? So it's a compound. You can vary the molar fraction. So when you vary the molar fraction or the fraction of the element in the compound, you effectively alter the lattice constants of the compound as well. So if you're talking about growing this compound, that consists of 3 different materials on a substrate. So you need to know the lattice constant of the compound in comparison to the substrate in order to calculate the lattice match or lattice mismatch. Right, so many informations on this page, right? You can come here. Okay, you can see here. So I'm pointing now to silicon germanium. See, you can see you can grow epitaxial germanium on silicon, and then you can. So the film is on the top one, the dark gray, and then the substrate with slightly different lattice constant is in light gray. So if you combine together, they look like this, or they can be relaxed germanium as well at the interface. You can see here it's a bit relaxed, and it goes back to the normal condition on top. Right, the interface, the very interface is the very crucial one, where you combine silicon, you bond germanium to silicon atoms, right? Nanti boleh datang sini dan baca. So look at the calculation here, the lattice mismatch equation. So lattice mismatch at the interface of indium arsenide, epi layer, right? Epi layer, the thin layer on gallium arsenide. So we are now growing in S on gas, on gallium arsenide. So the mismatch is given by, so the constant of in S, the epi layer or the film, minus the substrate over the substrate, just like what we did for germanium and silicon just now. So that will give us about 7%, which is, I think, relatively big, especially if you compare this now with silicon germanium, which is only about 4%. Okay, so the constants are given. So right, tengoklah kat sini ya. Anybody working on XRD to determine the lattice constant in your FLP? Ada ke buat XRD? Anyone working on XRD? Ada. Okay, Juara, you guna XRD for what? Is it for lattice constant related stuff or something else? Crystal structure, yeah? You want to determine the crystal structure. What's your material? What's your material yang you nak SRD tu? Chalcone. You buat dengan Dr. Suhana FYP Dr. Suhana ke? Prof. Razak? Okay, right. Chalcone typically under X-ray lab lah. So you're looking into the crystalline properties of chalcone, yeah? Okay, good. Right, so done. Let me go back to the slides. Right, coming back to the slides now. What time is it? 10:30. All right, half an hour to go. So you can see the slides now. Nampak kan? Nampak lah semua slide? Before I continue? Okay, right, good. So yeah, this is the calculation just like the equation we saw on the pages now for indium arsenide and gallium arsenide, right? So in this case, the mismatch of germanium and silicon is about 4.17, 4.27. So good, done, clear. So let's continue then. When a narrow band gap material meets a wide band gap, so when we are combining the two different band gaps to form a heterojunction, 3 situations may happen. Okay, we will end up in 3 situations. we call them as straddling, staggered, or broken gap, depending on the type of band gaps that we are combining. For example, if you look at the straddling case, case A, straddling, sorry. So look at the band gap of the two different materials. So on the left hand side, the black one is the narrow and the blue one is the wide, right? So narrow plus wide. Narrow and wide. Narrow band gap, wide band gap. So if you want to know whether they're going to end up as straddling or staggered or broken gap, we need to know the value of EC and EV of both materials. Okay, so for this case, for straddling, the EC and EV lie within the EC and EV of the wide band gap. Maksudnya, the EC here and EV here are within the boundary of EC2 and EV2, if like. Say, let's call this S1 and 2. So EC1 and EV1 are within EC2 and EV2. So they are right within the wide band gap. So we call that as a straddling case. The second case, look at this. Now the EC1 is higher than EC2, but the EV1 is within EC2 to EV2. So EV1 duduk kat dalam ni, but EC1 is slightly above EC1. So we call that as staggered band gap, right? The third situation is when both EC1 and EC2 are beyond EC1. Dua-dua duduk atas. Okay, dua duduk atas, yang narrow band gap, dua-dua EC-EV duduk atas wide band gap, right? So in this case, we call the combination as a broken gap. Okay, so you have to really know the EC and EV levels of both materials, right? 1 and 2, narrow and wide. So let's look at the band diagram. NP heterojunction between narrow N-type and wide band gap P-type. So look at the notation here, NP. N is small, P is capital. Apa maksudnya? So means the N there is the narrow band gap. Small letter means narrow band gap. P there is used to signify wide band gap. Wide band gap, eh? So if you have the opposite case, for example, then you're going to end up writing NP. Wide N, narrow P on the opposite case, okay? So in this case, we're talking about narrow N and wide P, therefore small n, capital P. So we're trying to combine them as a heterojunction. So let's have a look at the band diagrams before the contact and after the contact, after thermal equilibrium to be more specific. So if you look at the band diagram on the left, so which is the case for this? Is it straddling, staggered, or broken gap? Look at the band diagram on the left and compare this. Compare this. Are we working on straddling, staggered, or broken gap? Straddling, and very clear cut, right? So both the EC and EV1 are within EC2 and EV2, right? So dia duduk dalam kan, right? So let's look at the band diagram before and after the combination. So first draw the vacuum level and then draw the EC and EV for material number 1 on the left, and then EC and EV for material number 2. Draw the Fermi level accordingly, and then look at the Fermi level for the N-type. So it's close to a conduction band of the germanium. So in this case, germanium is the N-type, germanium, and gas, gallium arsenide, is the P-type. Here we are combining germanium on gallium arsenide. Okay, so you should be able to calculate as well. You just go back to the lattice constants of germanium and gallium arsenide and do your lattice mismatch calculation accordingly based on the given information, right? Then EC, EV done, EF done. right? So straddling case, so both are within. So draw the vacuum level, label the electron affinity for both cases, left and right. Draw the work function as well. Work function is given by the distance between vacuum level to Fermi level. Okay, Fermi level to vacuum level. Work function. Draw the affinity as well. Electron affinity is given by the distance between the conduction band to vacuum level. Okay, label accordingly. Then done. Right? So, and then label this difference in EC and difference in EV. Okay, to signify how narrow is the band gap within the wide band gap at the interface. Okay. Then this is before the combination. So after they are combined together and thermal equilibrium is achieved, so thermal equilibrium is achieved means you have got the diffusion of carriers and all those stuff thermal until thermal equilibrium. So this is how it looks like. So the vacuum, note that the vacuum level is slightly distorted. Okay, distorted. So it follows the EC of, so dia punya ni dia follow dia punya it follows the EC of both materials on the left and on the right. Tengok kat sini. Dia follow ni EC of both materials slightly ikut the profile lah. Okay. So note everything, the depletion width, for example. In this case, the whole depletion region is made of N side here, the N side germanium and P side gallium arsenide. Okay. Note the single Fermi level. So see single Fermi level, even though it's labeled as EFP on the right, EFN on the left, but it only forms a single Fermi level, single chemical potential upon thermal equilibrium. Okay. So yeah, and then the VBI, the very high in gallium arsenide, and then also the VBI in germanium. Okay, the band gap in gallium arsenide, the band gap in germanium, and then the EC, the difference of narrow and wide band gap, the difference in EV. Okay, pretty much the same thing, the same information need to be retained after thermal equilibrium, except you have to beware of a single chemical potential or chemical, the Fermi level, right? Fermi level, and the rest should follow accordingly. And then you need to also label the depletion width and space charge. Right, so energy band diagram. So let me just finish this off in the next few minutes. So energy band diagram to reach thermal equilibrium, where EF is a line single chemical potential, electrons from the narrow gap n-type, just like what we discussed in forming p-n junction in the last few lectures, right? So in order to reach thermal equilibrium, electrons in the n-type will see a concentration gradient at the junction. Holes in p-type will also see a concentration gradient at the junction, and then both will diffuse to the opposite side accordingly until thermal equilibrium is achieved, right? Electrons from the narrow gap n-type and holes from the wide gap p-type must flow across the junction due to the concentration gradient. Exactly like our p-n junction, because this is also a p-n junction, except it is a heterojunction, but our last one was homojunction. But the physics are the same, right? Concentration, not depletion, sorry, concentration gradient. Okay, concentration gradient. Then thermal equilibrium is achieved. The flow creates a space charge region in the vicinity of the junction, just like what we discussed last time. Space charge region, SCR, and also called depletion region, O equals to W, right? On both N side and P side, okay? Space charge extends into N-type, Xn, and P-type, Xp. So the whole width will then be given by Xn plus Xp, just like the p-n junction last time. So the discontinuities in the conduction and valence band and the change in the vacuum level are shown in the figure, right? So you can see the discontinuity in EC and EV, which are labeled as this. this, the EC and EV. The delta is the discontinuity that is expected when you combine narrow and wide bandgap as a heterojunction. So EC and EV, and also the vacuum level. The change in vacuum level is also illustrated here. We also discussed this now, this one. Okay. Following the profile of EC, right, due to the thermal equilibrium condition. Gonna practice draw this, okay? Try to practice drawing this before thermal equilibrium, before the combination and after the combination. And try to also explain what happens, just like the way you explain for p-n junction before thermal equilibrium is achieved. And then if there is a question on this, you may also be asked on lattice mismatch calculation. For example, in this case, germanium over gallium arsenide. And then what is the expected lattice mismatch? And then you should be able to do that, just like what we did just now, right? So one example, heterojunction silicon solar cell, just like what we discussed yesterday. There are many more devices available which are based on heterojunction, but this is only one example, just to illustrate the heterojunction nature, okay? So we also saw this yesterday in a different diagram. So have a look at this now. We have a central wafer. So before this, we have been discussing about having a wafer p-type, for example, or n-type. Say if you have a p-type, then you diffuse a very thin layer of emitter to form a junction. So you have an n on p, and that's it. You have a single p-n junction. Another form of junction is also called pin junction. Okay, this is another thing. You may have p-n junction, and you may have another form of p-n junction which is called pin junction. It is also a p-n junction, except you insert, Rafael, you know, right? So it's the very same thing like p-n junction, except it's an extended version of junction. So rings a bell, huh, Rafael? Okay, except you include a very thin intrinsic layer in between. So this is what makes the Panasonic solar cell technology, right? So it's based on pin junction, intrinsic in the middle. So you don't necessarily use pin junction as it is. You can also insert an intrinsic layer, thin one in between, in order to use the same pin junction, except you have a very intrinsic layer in between. Okay, so let's have a look. So you have n-type in the middle, n-type crystalline silicon, 1.12 electron volts. Crystalline silicon, yeah, n-type, right? So let's look at the bottom part first. Look at the bottom part first. So below crystalline silicon, we need to deposit atas dia, bawah dia, 5 nanometer of intrinsic amorphous silicon hydrogenated. So H here means hydrogenated. H. I here means intrinsic, so it can also be n-type or p-type, but in this case, it is intrinsic amorphous silicon, amorphous 1.8 electron volts, right? So it's already a heterojunction then. But in this amorphous, we also use hydrogenated amorphous, means nanti you akan belajar, you're going to learn this more when we talk about deposition process in fabrication. Hydrogenated here simply means when you deposit the amorphous silicon, you include some hydrogen gas. That's all. For some function, for some role. Okay, it's more of the surface preservation punya function. The role is for surface preservation, to be more specific, to saturate the dangling bonds on the surface of the crystalline silicon. So intrinsic silicon followed by n-type n plus amorphous silicon hydrogenated as well. So still 1.8 electron volt, but now is n plus. So now we are moving from n to I to n plus, and then we move to ITO with which is a transparent contact, which is a form of TCO, an example of TCO, followed by a silver contact at the back. So on the front side, if you look at the front side, so we can see intrinsic as well. So 1.8 electron volt as well, another heterojunction. So you have junction at the front, junction at the back. okay? Then followed by P plus. So this is the pin thing, okay? So this is the pin in the device, in the junction. P plus I N. So you form a pin junction in this case, a pin instead of PN. Essentially, it is a junction as well, except you have a very thin layer, like 5 nanometers of intrinsic to serve some role, okay? Then you have the very same ITO and AG on the front, okay? Except AG on the front is not covering the full surface because it is a metal contact. We're going to learn later on. After this topic, we're going to jump into solar cell, and then we're going to continue with your presentation next week. And then after the presentation session, I'm going to continue with MOSFET to finish off the course, right? So kita akan tengok next week, why do we have this contact like that, and why do we have the full contact like this at the back, okay? So you can see now the pin. So let's translate all this into the Venn diagram of this device. So you have metal on the front side. Okay, ini front, front is on the left, front, back there, back. Okay, so you have P plus on the front, and then you have intrinsic, and then you have N-type. So look at the Fermi level there across the device, okay? P-type, so close to VB, intrinsic close to mid-gap, EF for N-type in the middle close to EC, and then it crosses to intrinsic close to mid-gap. Well, it's not drawn properly. It should be closer to the mid-gap by the right drawing. This one is not so accurate though. N plus is close to EC and then the metal, okay? So you can see the EC, delta EC and delta EV, delta EV, delta EC. This is the discontinuity at the junction due to the heterojunction nature. Discontinuity, discontinuity at junction, delta EC and delta EV. So you have crystalline silicon in the middle, amorphous silicon on top and at the back. So in this case, the light absorption, we're gonna discuss later on in solar cell. The light absorption is done in this bulk, in this crystalline silicon. So optical role is done in this bulk. Dekat pin, dekat atas ni, IN, IP, and IN is just to serve the electric field at the junction. Remember, if you have N dope and P dope, left and right, you're gonna have electric field. So electric field on the left and on the right, on top and at the bottom in this case, is to drive carrier separation in the crystalline silicon, okay? So that means we have learned about PN junction, but the application is not only limited to PN junction as it is. It may also be extended to pin and other device, other sort of architectures. We call it architectures, or the design or configuration to serve certain function or to serve certain roles in the actual devices. Okay, but what you learn about the PN is enough for you, is sufficient for you to extrapolate your knowledge, I would say, to relate with the real applications in the real devices. Okay, so you can also see this heterojunction by Panasonic. Let me just go to the website for the next few minutes and share with you. I've opened already the website of Panasonic, even though they are closing, they are withdrawing from PV business. Just share. So the same link I gave in the website, in the slide. So you can see the website now, can you? Okay, good. Right, so you can come to this Panasonic, or you can search Panasonic solar cell or something. Then it will bring you to this web page, okay? So if you want to know, the technology here is called heat, ataupun pin tadi tu is called heat, heterojunction intrinsic technology, right? Heat here is called heterojunction intrinsic technology, right? So it's based on pin junction. Heterojunction here means the combination of crystalline silicon 1.12 with amorphous silicon 1.18 on both sides, using pin as the device, as the junction architecture, I would say, right? So why heat and everything? So you can have a look at the application as solar roof, blah blah blah. Then I would like to show you this. The technology comes to this. You come to this technology tab. and then it explains to you about the technology itself. So the exact images I captured in the slide. Okay, silicon heterojunction, solar cell. So look at the ultra thin layers of amorphous silicon, so that which makes it intrinsic in nature. Okay, which makes it intrinsic in nature. So you have, say here, okay, let me just briefly go through this. Where is your crystalline silicon? Okay, the gray part here is the crystalline silicon. The central part, which does the light absorption, that's about 100 plus micron in thickness. And then it is sandwiched with intrinsic layer on top, I amorphous, and then at the back, I amorphous as well. And then you have amorphous layer of p-type on the front side and amorphous layer of n-type at the back side in order to form the pin junction, PIN, to be more specific. Oh, I forgot to tell you that just now. Hold on. Sorry, where's the website? Yeah, it's okay, it's okay. It's right, it's right. So TCO on the front and TCO at the back, and then you have your metal contact on the front. So these fingers here means kalau you pernah tengok solar cell lah, ataupun you search later on, you will see these fingers as a small, a thin metal line. The metal line is silver, but it's very thin. I'm going to discuss this one more and more in solar cell after this topic. So it's a very thin layer of metal yang nak extract the current. So we talk about the carrier collection probability, right? And we talk about the rule of metal to extract carriers for the case of solar cell. To withdraw electron on one side, hole on another side. So electron dan hole dia akan keluar through the metal. So they will travel through the metal contact, right? So they will first travel through these metal fingers here, the very thin one, and then they will be collected by a bigger road, if you like, the jalan yang lebih besar. So which is called tab or bus bar. Yang tebal ni, the vertical part I'm showing here is the bus bar or the tab, if you like. But the smaller part, the horizontal part, the perpendicular, that's called fingers, and thinner in nature, and the tab is wider and bigger in nature in order to collect more and more electrons. When you have more and more electrons arriving at the same point, so they need to be carried with a bigger wire, right? Kita pakai bigger wire kan kalau current lagi banyak kan. So at this point in the tab, you're going to end up with bigger current or larger current. So therefore, you need a wider tab in order to collect all those carriers to the outer circuit. Nanti kita akan measure kat belakang, dia punya junction box. I'm going to show you later on when we talk about solar cells next time. So yeah, you can go down. We have discussed before this in the principle. We have discussed about light absorption on the front, right? Remember, light absorption at the front. Let me finish in 2 minutes. Kita discuss on light absorption on the front side, and then you're going to have your junction on the front, and then light will be absorbed. Then electron hole pairs will be generated, and then they will be separated and then collected on the opposite side of the contacts. But when we talk about solar technology, I'm going to touch later on as well. The collection, the incident light may, what you call the light harvesting is not only done on one side. It can also be done on both sides, and in that case, we call it as bifacial solar cell. Bifacial means what? Dua muka. Maksudnya you absorb most of the incident sunlight here on the front side, but you also take opportunity of the reflected light at the back. Okay, reflected light. Kan kita pasang when you mount your solar panels on the ground or on concrete or on grass or on rooftop, so there'll be some portion of the light reflected yang tak kena, which do not hit the panel first time, but hit the roof, for example, hit the grass, hit the soil, hit the snow, hit the concrete. That will be reflected back. So the one that is reflected back, we call it as ground albedo. Let me write down here. Ground albedo. You baca if you are interested in this. I'm not going to teach you about this, but you check it out. Ground albedo is the reflection level of the ground, the soil, the grass, the concrete, the snow, the rocks, whatever, depending on where do you mount the solar cell or the solar panel. The reflection will be harvested at the back. So that means we have another phase at the back. We have another harvesting mechanism at the back. And in this case, we call this device architecture as bifacial. Oh, bifacial solar cell. I think time's up already, that's why. Bifacial solar cell design. Okay. Tengok kat sini, the conventional technology only hovers on one side, but the bifacial technology by Panasonic, and in fact, it's being manufactured by some other manufacturers as well. So you can also harvest the sunlight at the back by manipulating the backsheet reflection. In this case, the ground albedo that I'm saying. Okay, so this will increase the power from the panel by about 20% to 30% max, right? So typically people report about 10%, 15%, depending on where do you mount the panel. Kalau snow lain, concrete lain, grass lain, soil lain, depending on the ground albedo. And this will give you extra power from the panel or from the cell by about 15 to 20% average, I would say. Okay. So, okay, let me just finish this off. I think I'm done already with everything on the slide. Let me just check again to be sure. So, yep, that's the slide. Okay, so just go back and try to check for yourself on other examples of heterojunction devices. I believe some of you will be also will be mentioning this in your presentation next week as well. Okay, so you may encounter this in LEDs, for example, in some other semiconductor devices as well, which works based on heterojunction architecture. Okay, some devices you may find working on homojunction architecture. Some other devices may thrive on heterojunction architecture. So try to go back and search for yourself. So what are those examples of heterojunction devices other than the solar cell that I showed you just now? So yeah, that's it on heterojunction. Any question? Any questions? So far, okay? Can you follow? Is it good? Oh, good so far? Okay ke? Tak ada soalan? Alright then. So today is what? Tuesday. So we have 2 more days in this week. So tomorrow I'm going to continue with solar cell. Okay, I'm going to continue with solar cell. I'm going to show you how do we use the physics that we've learned so far to relate to device operation and then to relate to the manufacturing business worldwide. Okay, so it's going to be very interesting because you're going to learn on how to relate the physics to the applications of the devices. Then we're going to continue. I think I'm going to take about 2 or 3 lectures max on solar cells, and then we're going to continue next week with your presentation. Then after the presentation, I'm going to continue with MOSFET, and that will take about 1 week max, and then we're going to finish by week 14, I would say, right? And then I'm going to have a review class to review from the very first class until the final class. Right, ground albedo. What's ground albedo? Ground albedo is ground reflection, but we call it as albedo in PV, okay, in PV, in photovoltaics. So ground reflection depends on where do you mount the panel. Soalnya kita nampak panel ni, if you see the panel, you can see the panels are mounted on the roof. You can see the panels are mounted on concrete. You can see the panels mounted on, kalau you tengok large scale solar farm, yang solar apa ni power plant tu, dia panels are mounted on the ground, atas tanah kan. So you may also see panels that are mounted on kawasan yang berbatu, for example, rocky areas, small rocks, or on pavement, on snow, perhaps in snowy areas. Then these ground level, they have their own reflection levels. Okay, so ground albedo is important when you talk about bifacial solar technology, because you want to harvest the light at the back as well, on top of the front. So you harvest on the front just the way it is, but on top of that, you also harvest the incident photons at the back, because some of the incident photons are not striking on the surface first time. So dia mungkin lalu dekat tepi kan, tapi panel tak kena. Tapi upon the ground reflection, dia akan reflected at the back. Okay, kata ni saya punya tanah. Ground reflection, so you're going to have some reflection, say 15 to 20% of the reflection level. And then due to the reflection, some of the incident photons will be harvested at the back of the cell, right? Just like the bifacial technology that I showed you just now. So that's why in this case, ground albedo will be very important to know, right? So you have to know where do you mount the system in order to know what is the expected increase in the output power of your PV system later on. Okay, so typically people report about 15 to 20% of increase in the power of the panel due to the increased ground reflection, due to the bifacial technology punya effects, right? Which harvest the photons at the back as well, not only on the top surface. Is it okay, Gloria? So bila you tahu dia punya ground level reflection, then you can expect how much do I get the extra power from the panel. So you can do correlation of ground albedo versus increased power from the panel, and then you can study the correlation, whether it's okay or not, whether it's worth it or not. And in fact, bila you nak invest your money in certain panels, certain systems, certain industries, you want to know the return on investment. Okay, return on investment, ROI. Return on investment. I invest this much, berapa lama nak balik modal? So how long will I get the money back? And eventually I'm going to generate profits after that, right? So this is how you relate all the techno-economic perspective of the knowledge, right? The techno side, the technical side, and then the economic side and the real life application. Okay, so I'm going to see you tomorrow. I've uploaded already the slides on solar cell. So let's move on to solar cell. All right, bye-bye. Take care. Assalamu alaikum.